Effect size in statistics is a way to understand how big or strong a change or relationship is in a research study. It answers the question, how much difference does this really make? Rather than just is there a difference? For example, a company introduces a new employee training program and wants to know if it improves work performance. The traditional statistical test, like a p-value, might say the results are significant, meaning the change probably didn't happen by chance. But that still doesn't tell how big the improvement is. Effect size steps in to describe that part. It tells how large the improvement really is and whether it matters in a practical sense. So, while the p-value tells whether something is real, the effect size tells whether it's worth paying attention to. Why effect size matters. Effect size helps researchers, managers, and policymakers judge the strength of results beyond numbers. Two studies can both be statistically significant, but one could show a very tiny effect that means little in real life, and the other could show a major improvement that really changes outcomes. For example, if a company changes its work schedule to reduce tiredness among employees, a small effect size would mean that productivity only increased a little. That small change may not be worth the effort or cost. But a large effect size means that productivity clearly went up, showing that the new schedule really helped and made a meaningful improvement. There are different ways to measure effect size depending on the type of data and what the research is studying. Cohen's d. Cohen's d is used when a researcher wants to see if there is a difference between two groups. It works best for large samples and when both groups are about the same size. For example, a psychologist may compare the average stress levels of people who meditate versus those who do not. To calculate Cohen's d, we need the average, mean, score of each group, the standard deviation, which tells how spread out the scores are in each group. Then, Cohen's d is found by dividing the difference between the two averages by the average spread of both groups, called the pooled standard deviation. D equals 0.2 means small difference, D equals 0.5 means medium difference, D equals 0.8 or more means large difference. Glasses delta is used when one group scores very much more than the other. It is common in healthcare research, where one group may have a treatment and the other is a control group. For example, a nurse may compare the average blood pressure of patients who received a new drug versus those who didn't, but one group may have more variation. To calculate Glasses delta, we use the average of each group, the standard deviation of the control group only, the group that didn't receive treatment. This method uses only the control group spread because it gives a fairer comparison when the two groups have very different levels of variation. Hedges G is used when the sample sizes are small or uneven, such as when one group has 10 people and another has 30. For example, a business researcher might compare the sales performance of two small teams that tried different marketing methods. Because the groups are small, Hedges G gives a more accurate result than Cohen's d. To calculate it, researchers need the average, mean, of each group, the standard deviation of each group, the sample size of each group. Hedges G corrects for small sample bias. When the samples are big, it gives almost the same value as Cohen's d. Pearson's R, correlation coefficient. Pearson's R is used to find out how strongly two things are related. It doesn't compare groups, instead, it shows how one variable changes when another one changes. For example, in business, a manager may want to see if higher employee satisfaction is related to better customer service ratings. To calculate it, the following are needed: values of both variables, for example, satisfaction scores and service scores, the sample size, number of observations, the standard deviation for each variable. Pearson's R gives a number between -1 and +1. +1 means a strong positive relationship, both go up together. -1 means a strong negative relationship, one goes up, the other goes down. 0 means no relationship. Cramér V is used for categorical data, which means data divided into groups or labels, not numbers. For example, in education research, a teacher might check if students' preferred learning style, visual, auditory, kinesthetic, is related to their subject choice math, science, art. To calculate Cramér V, the following are needed: the chi-square value, x superscript 2, from the test of independence, the total sample size, n, the number of rows and columns in the data table. When interpreting Cramér V, the value always lies between 0 and 1. A value of 0 means there is no relationship between the two categories, while a value close to 1 means a very strong relationship. The size of the effect depends on the degrees of freedom, dF, which are based on how many categories are in the data table. For example, when dF equals 1, values around 0.1 show a small effect, 0.3 a medium effect, and 0.5 a large effect. When dF equals 2, smaller numbers mean the same thing, around 0.07 is small, 0.21 is medium, and 0.35 is large. As the number of categories increases, the cutoff for what counts as large becomes smaller. So, even a V of 0.25 can be seen as a strong relationship when there are many categories. Cramer's V only shows how strong the connection is, not the direction, positive or negative. When reporting it, researchers also show the chi-square value, degrees of freedom, and p-value. When should you calculate effect size? Effect size should be calculated both before starting a study and after collecting the data. Before starting, it helps in planning how many people or samples are needed. This is done through something called a power analysis, which checks if the study is strong enough to find a real effect when it exists. If the study has low power, it might miss an important effect even if one is truly there. After finishing the study, calculating the actual effect size helps show how strong or meaningful the results are. Researchers also use these values later in meta-analysis, where results from many studies are compared to see the overall strength of an effect across different research areas.